So now modeling thermal noise. How can I model this thermal noise? And thermal noise is also often described by the term white. You know, white light contains all the wavelengths, right? So in wireless, we deal with frequency, but in optical, we deal with wavelength. So in optical, we deal with lambda. In wireless, we deal with frequency. So white indicates a light which has all the colors, all the 7 colors in it. So here also the thermal noise, we say that the thermal noise is going to affect all the frequencies, right? So you can relate thermal noise to white. So how we say white light in optical or in terms of wavelength, we can call thermal noise also often described as white. So white indicates that it affects all the frequencies uniformly, but it is not exact because in wireless we don't use the term white. So we generally use the term thermal noise, but to understand or relate this with the light, we can relate this thermal noise to white. And available noise power. So the term available noise power, whatever we have studied, PNA, is the maximum power which can be delivered to the load. So we have a simple diagram here. So you have a noise voltage and you have a load R. The maximum power is delivered from this noise voltage to the load only when this resistance value is also equal to R. This is given by Thevenin's theorem. You know that when in a Thevenin's theorem, if you want maximum power transfer, the source resistance and load resistance must be same. So if the load resistance is going to be capital R, then the source resistance must also be capital R to ensure maximum power is transferred from source to your load. So there, whatever the term available noise power we have been discussing so far, that is the maximum power which is transferred to your load. Okay, so that PNA, whatever we have studied in the formula, right? PNA refers to the maximum power which can be transferred to the load, which is denoted by this simple network having a source resistance, having a load resistance R. So here both the values are equal to R, indicating maximum power transfer of the noise from source to your load. And we have seen one formula for thermal noise in terms of the temperature and bandwidth. We have also have one more formula for thermal noise in terms of the circuit, whatever we have seen. So in this circuit, the maximum power is going to be En square by 4R. How we get that? See, I have a loop here. Voltage source is En. The resistance are R and R in series. So total resistance is 2R. So I can write current I is equal to En by 2R. Okay, so current I is equal to En by 2R. And you know power equal to current I square into R. So the current is En by 2R. So square it. So En square by 4R square into across what you are measuring the power. I'm measuring the power across resistance R. So multiply that by R. So 1 R you can cancel. So you will get En square by 4R. So that is how you get the expression for power from this circuit. So En square by 4R is the noise power from this circuit. Actual expression for noise power what we have is KT del F. So I'm going to equate